Good morning, students. Myself, Vijay Shankar from ECE Department, Chevrolet Engineering College. Today, we are going to discuss about the inductance. The last class also we discussed the inductance of solenoid, inductance of toroid. And today's class also, we can discuss again the inductance of solenoid, inductance of toroid, and inductance of the coaxial cable, and magnetic energy density. Magnetic energy density also. See the inductance. When a coil with N turns carrying current I, the flux is produced by it. This flux linkage links with each turn of the coil. Thus, the total flux linkage of the coil having N turns or N5 Weber turns. The flux L is equal to, inductance means the ratio of, what is the inductance? The flux linkage with the coil is proportional to the current flowing through it. The ratio of total flux linkage to the current producing that flux is called an inductance. The ratio of total flux linkage to the current. What is the total flux linkage? N5, and the current, whatever the passes to that coil. The ratio of total flux linkage to the current producing that flux is called inductance, and it is denoted by L and is measured in L. Okay. First one is inductance of the solenoid. Inductance of the solenoid. Consider a solenoid of N turns. Let the current flowing through that solenoid I. Length of the solenoid be the L. Length of the solenoid be the L. And the cross-sectional area be the A. The current I is passes through the coil, and the solenoid length is L, and area of cross-sectional is A. The field intensity inside the solenoid, the field intensity, nothing but the magnetic field intensity, H. Inside the solenoid is H is equal to the number of turns of the solenoid N, and whatever the current that is passes through that coil I by the L. Okay. H is equal to Ni by L, ampere per meter. The current is amperes and L is the length in terms of the meters. And the total flux linkage is given by, how to find out the inductance. Inductance L is equal to N5 by I. N5 by I. The total flux N5. Phi is nothing but about the magnetic Gauss law for the magnetic field, B bar dot ds bar. Otherwise, phi is equal to B integral ds. What is the integral ds? Is nothing but the area of BA. So N phi is equal to N into B into E. So what are we have? The number of turns. B is the magnetic flux, and A is the area or integral of ds. And you can change the magnetic flux into the magnetic field N into mu H A. What is the H? We got Ni by L. N into mu Ni by L into A. So N square, therefore N phi is equal to, we got n square mu I A by L. A by L. But we need to find the inductance. L is equal to the total flux linkage by the current. N5 we got is a n square mu I by A, n square mu I A by L whole divided by I. So I get cancelled. Finally, the inductance L is equal to n square mu A by L. Mu A by L and n square mu A by L, where n is the number of turns and mu is the permeability and A is the cross-sectional area of the solenoid and L is the length of the conductor. The capital L is the inductance. Okay, my dear friends. See mu into n square A by L. The inductance L is equal to mu n square A by the L. The inductance of the solenoid. Next, inductance of the toroid. See, consider a toroid ring with the n turns carrying current I. Let the radius of toroid be the capital R. See, this is a toroid we have, and there's a number of turns of the coil. The current I is passes through that coil, and the radius of that toroid is a R. Okay. So the magnetic flux inside the toroid ring is given by magnetic flux density, or the magnetic flux density, or we can find it out is in terms of the magnetic field. What is a magnetic field? H is equal to N into the number of turns and the current I. Previously, we find that we wrote that it is a L. L is the length of the solenoid. Now it is a 2 pi R. The toroid ring with the radius of R. So B is equal to the relation is mu into H. Then it becomes of mu N I by the 2 pi R. The total flux linkage of the toroid ring, the total flux means N phi. N phi. Where phi is again use the B into A, N into BA, where B is a mu Ni by the 2 pi R into A. The total flux linkage is a mu N square IA by the 2 pi R. Mu N square IA by the 2 pi R. And the inductance is total flux linkage by the total current. Total flux linkage by the total current, where total flux linkage we got mu N square IA by the 2 pi R, and the total current is I. I get cancelled. The inductance L is equal to mu N square A by the 2 pi R, and where A is the area of the cross section of the toroid ring, and R is the radius of the toroid. Where A we can take it as a radius of pi R square. You see, by using this diagram, the radius of the cross section of a ring. Cross section of a ring. See here, the dark line we say is a dark line. The cross section area of the ring is the radius R. That we can use the pi R square, where A is a pi R square. L is equal to mu N square A by the 2 pi R. Got it, my students? So previously it is L is equal to solenoid is a mu N square A by the L. Now for the toroid is a mu N square A by the 2 pi R. Got it, my students? If the toroid, for a toroid with the n number of turns and height, H is the height of the toroid, with R1 is the inner radius and R2 is outer radius, the inductance is. So we are not taking here, it is a capital R, the total toroid radius. if the inner radius of the toroid is R1 and the outer radius is R2, that R we can now, it is a ln of R2 by R1. ln of R2 by R1, and A is becomes a H, mu n square H by the 2 pi ln of R2 by the R1. Okay, the inductance of toroid. Now the third one is inductance of a coaxial cable. We already know the coaxial cable equation is H is equal to I by the 2 pi R into AR bar or the A5 bar. So with the inside there is a current inside the radius of radius is A, and outermost there is a 2 circles with the radius of B, and with the radius of R is a Gaussian surface. Okay, so H is equal to, for a coaxial cable of field intensity at any point between the inner and outer conductors is H is equal to I by the 2 pi R. We already derived this equation in the range of A to B. R is greater than the C and R is in between, and the R is less than the A is the second case in between of R and the B. H is equal to I by the 2 pi R, and B is equal to mu I by the 2 pi R. Got it, my students? And it is along with the phi direction of H. H is nothing but is actually, it is a phi direction, and B bar we consider as a vector. B bar is equal to mu I by the 2 pi R into A5 bar. And substitute this B bar in the total magnetic flux. The phi is equal to B bar dot ds bar. B bar dot ds bar. Gauss law of magnetic field intensity. ds is along the phi direction, the cylindrical coordinate system, dr dz into A5 bar. Okay. In the Gauss law, the B bar dot ds bar as a phi is equal to the B bar we got in the coaxial cable mu I by the 2 pi R, or the 2 pi the small r into A5 bar, and in the cylindrical coordinate system along the differential surface area normal to the phi direction, because here the phi is only there. So dr dz into A5 bar. In this integral, A5 bar dot A5 is a 1 mu I by 2 pi R into dr and dz. Okay, so dr is the radius of A, and the radius of B is there. Inside there is a radius of A, outside the radius of B. So mu I by the 2 pi considers a constant. R values, R is equal to from A to B, 1 by R into dr, and Z is length of that axis is a D. So it starts from the Z is equal to 0 to the D. Got it, my students? In the coaxial cable, the diagram showing here, see the radius distance is the D. Is the D, my students, so D, and the radius of inner cable is inner circle is A and outer circle is B. So the Gaussian surface is in between of A and B. Okay. So the integral of Z is a dz. Phi is equal to, what is a phi now? The phi is equal to mu I by 2 pi, mu I by the 2 pi, and 1 by R is ln of upper limit is a P and lower limit is a A. So it is a minus means B by A, and dz, integral dz is a Z, upper limit is D, lower limit is a 0. So we will get only the D. So phi is equal to, and total flux so where phi we got n into mu I by 2 pi ln of B by A into D whole divided by the I. So I get cancelled, where L is equal to, therefore the L is equal to, we got n mu by the 2 pi mu into D also ln of B by A. The coaxial cable inductance of a coaxial cable. Okay, my dear students. CL is equal to. So here there is no any N value. So the total flux, what we derive here, there is no any N. Only the phi is there. Here also the N. Mu D by 2 pi into ln of B by A. Okay, my dear. Next, the very important topic, magnetic energy. In the electrostatics, we studied the electric energy. What is electric energy? W is equal to WE is equal to. So here the M is nothing but the magnetic energy. Here it is a electric energy. 1 by 2 CV square. CV square. We already derived this equation. Now the magnetic energy is 1 by 2 Li square. Li square, where the C is the capacitance there. Here we are finding out the inductance and to the current. Okay. So see, similar to the capacitor studied previously in the electrostatics, inductor is also an energy stored element. In a capacitor, the energy is stored in the electrostatic field, while in the inductor, the energy is stored in the magnetic field. So in the capacitor, the energy is stored in the electrostatic field, while in the inductor, energy is stored in the magnetic field. The energy stored by inductor is given by Wm is equal to 1 by 2 Li square, inductance and the current. Consider a differential volume in magnetic field B bar. Consider a differential volume in magnetic field B bar as shown in this figure. Consider that the top and the bottom surfaces of a differential volume conducting sheets. See, consider this is on the XY plane, there is a one sheet is there, opposite another sheet. Upward, topmost you can consider as a conducting sheet 1 and the bottom sheet is considered as a conducting sheet 2. Consider that at the top and the bottom surfaces of the differential volume, conducting sheets with the current delta I are present. Delta I are present. See, from the definition of the inductance, we can write as L is equal to, we know the L is equal to the total flux linkage N phi by the I. Here there is no any n number of turns, so L is equal to phi by the I. I assume that it is a small differential inductance delta L is equal to differential phi and differential current, delta phi and the delta I. Delta phi is equal to, we know, according to the Gauss law, B bar dot ds bar. B bar dot ds bar. So phi is equal to, otherwise is a B into ds. So I'm assuming this is a small differential phi. So B into, it is also a differential surface. Delta phi is equal to B into delta S. So B into delta S by the delta I. According to the Gauss law of phi is equal to B bar dot ds. Differential surface area means, what is the differential surface area? Here, it's a cube, let us see here. From the figure, we can observe delta X and the delta Z, which is not passes the current. Delta X and the delta Z. Consider this sheet here, delta X and this one is a delta Z, the product of. Okay. So where the differential surface area is a delta X into delta Z. Delta L is equal to, now delta L is equal to differential surface area, the small differential surface area delta X we can consider as delta X into the delta Z whole divided by the delta I. Okay. What is the relation of B and mu? B and H is a mu into H. So change this B as in terms of the H, mu H into delta X, delta Z whole divided by the delta I. Got it, my students? Now we got this function. Delta L is equal to mu H delta X into delta Z. Now, on the XY plane, there is a sheet is there which is passing the current I. So delta I is equal. Now the differential current delta I can be expressed in terms of the magnetic field intensity H. The current flowing through the conducting sheets present at the top and the bottom is in the Y direction. In the Y direction. So delta I is equal to H into delta Y. Delta I is equal to H into the delta Y. Substitute that H is equal, delta I is equal to in the denominator, delta I is equal to H into delta Y. So delta L is equal to, since the current is passes in the Y direction, delta L is equal to mu H delta X delta Z and whole divided by delta I is H into delta Y. Okay. Now the energy stored in the inductance of a differential volume is given by, the Wm is equal to half 1/2 L into I square. Here also you can write it as a small differential elements or incremental values. Delta omega Wm is equal to 1/2 delta L and delta I square. Delta I square. Substitute this value here. One by 2 into mu H delta X, delta Y, delta X and delta Y, delta X and delta Z, H into delta Y, and delta I square. What is the delta I here? H into delta Y. So H into delta Y whole square. Substitute these two equations. This is a delta L and it is a delta I. Substitute these two equations in the delta omega M, Wm, not the omega. Delta Wm is equal to 1/2 mu into H delta X delta Z whole divided by H into delta Y. And what is a delta I is equal to H into delta Y whole square, because it is I square. So in this function, H and H get cancelled and delta Y and here one delta Y is get cancelled. The remaining function, incremental Wm energy stored in the magnetic is 1/2 into mu is there, mu H into delta X, delta Y and the delta Z. Delta X, delta Y and delta Z. So in the Cartesian coordinate system, dx, dy, dz is a volume, differential volume. dv is equal to the product of x differential element, y differential element and z differential element. So this also you can write it as a incremental volume 1/2 into mu H delta V. Mu H into delta V. Got it, my students? A small differential delta Wm is equal to, now we got as 1 by 2 mu H into delta V. Got it, my students? So it is a D incremental. Apply the integral on both sides. We'll get the omega m is equal to Wm is equal to 1 by 2 mu H into dV on. Okay. See, delta x, delta y, and delta z is a delta V. And delta Wm is equal to 1 by 2 mu H square into delta V. And Wm is equal to, as of limit delta V tends to the 0 and delta V by delta, bring that it is a delta V in the denominator, 1 by 2 mu H square. 1 by 2 mu H square. Here the H square is there. If 2 get cancelled, H square into 1. Okay, Wm is equal to 1 by 2 mu H into H. Mu H square, you can write it as mu H into H. What is a mu and H is a B on. So the relation between the energy stored, magnetostatics energy density Wm is equal to 1 by 2 mu H into H. Actually, it is a 1 by 2 into mu H square. What is a mu H is a 1 by 2 into BH. Wm is equal to. And Wm is equal to only in terms of the mu H square is in terms of magnetic field, and B and H is a magnetic field and the magnetic flux. And only in terms of the magnetic flux is 1 by 2 into. Change H is B by the mu. As omega m is equal to Wm is equal to 1 by 2 B square by mu. Only in terms of B square and only in terms of H square and the B and H. Okay. Integral E bar dot D bar, like that. So E bar dot D bar, Wm is equal to 1 by 2 the integral B bar dot H bar. So same thing in the electrostatic is 1 by 2 integral E bar dot D bar. E bar dot D bar. Same Wm is equal to 1 by 2 the integral B bar dot H bar into dV. 1 by 2 is equal to mu H square, and that is equal to 1 by 2. The same thing in electrostatic also, 1 by 2 into integral E square into epsilon, because D bar is equal to epsilon into E bar. Otherwise, 1 by 2 into integral D square by the epsilon. Now, instead of E and D, it becomes of H and B, 1 by 2, the integral of, here all the dV is also there, integral of B bar dot H bar into dV. So only in terms of magnetic field integral, instead of epsilon we got the mu, and E is there in the electrostatics, H is the magnetostatics. Magnetic field mu H square into dV, and that is equal to 1 by 2 the integral, when the D is here, D is a electric flux density and the magnetic flux density is a B square by the mu into D. So 1 by 2 the integral of B square by mu into D. So energy stored. Got it, my students? It's a very, very important energy stuff, magnetic energy and electric energy. In terms of E bar and D bar, and you can derive the in terms of B bar and H bar. B bar and H bar we derive by using the equation of omega Wm is equal to 1 by 2 L I square. And from these equations, we derive the Wm is We is equal to 1 by 2 Cv square. The capacitance, and here the inductance. Got it, my students? So with this, the completion of the magnetostatics, and we go for the next topics, in the magnetostatic, that is time varying fields and the Maxwell's equation. Time varying fields and the Maxwell's equation. Okay. So Maxwell's equation, we already derived that two Maxwell's equation. One is del dot d bar is equal to rho v and b bar dot ds bar is equal to 0. So one is Gauss law of magnetic field, another one is Gauss law of electric field. So in this Maxwell's equation, there is a 4 Maxwell's equation. One is Ampere's circuit law, Faraday's law, Ampere's circuit law, and Gauss law of magnetic field and Gauss law of electric field. The 4 Maxwell's equation. So what is a Faraday's law? According to the Faraday's law, a static magnetic field cannot produce any current flow. But with a time varying field, an electromotive force induces with which may be drive according to Faraday's experiment, a static magnetic field cannot produce any current flow. But with a time varying field, see here, up to now we did discuss about the magnetostatics, which is not a time varying fields. Here, a time varying fields independent of the variables, and here the dependent time varying field. An electromotive force EMF induces which may be drive a current in the closed path or a circuit. This EMF is nothing but a voltage that induces from changing magnetic fields or motion of conductors in a magnetic field. Okay. So what it states that E is equal to electromotive force EMF E is equal to a change of flux. A change is equal to the rate of change of, or the time rate of change of magnetic flux. Faraday's law discovered that the induced EMF is equal to the rate of change of magnetic flux with respect to the time, or to the time rate of change of magnetic flux linkages with a closed circuit. So E is equal to, here there is a number of turns of the circuit and the negative sign is always in the opposite direction. Okay. So E is equal to minus N into the change of magnetic flux with respect to the time. Minus N into d phi by the dt. Let us single turn circuit, N is equal to 1, E is equal to minus d phi by the dt. The Faraday's law states that a change of flux with respect to the time is induced EMF. The minus sign indicates that the direction of induced EMF is such that to produce a current which will be produce a magnetic field opposite to the original field. That is, a negative sign is the direction is a different. Okay, we already know the potential. The potential is E bar dot dl bar is equal to minus V. The induced remains here, that minus it becomes as a plus here, the E is equal to integral E bar dot dl bar. And the phi is equal to, according to the Gauss law, the phi is equal to B bar dot ds bar. We know these two equations. Okay. In the scalar quantity measured in the volts, the E is equal to integral E bar dot dl bar. So V is equal to actually the minus integral E bar dot dl bar. Right, in the induced EMF E is equal to also the E bar dot dl bar. So what is the induced EMF is minus d phi by the dt. So integral E bar dot dl bar is equal to, the induced EMF is minus d phi by the dt. What is the phi here? The integral B bar dot ds bar. Okay. From the Gauss law of a magnetic field, the magnetic flux phi through the specified area is given by the phi is equal to integral B bar dot ds bar. So E is equal to, now I am writing this is a E is equal to integral E bar dot dl bar, and E is equal to B bar dot ds bar using the relation of the equation 2. So E is equal to minus d by dt of the phi. Minus d by dt of the phi is there. The phi is nothing but integral B bar dot ds bar. They bring that is inside the value. So the E is equal to, we know the integral E for E bar dot dl bar, that is equal to phi is equal to, not the phi, and EMF E is equal to d phi by the dt, that is equal to minus d by dt of the integral surface integral B bar dot ds bar, B bar dot ds bar, and bring this inside the integral. It becomes of minus integral of dou B bar by dou t. Normal derivative becomes a partial derivative ds bar, and the same E is equal to E bar dot dl bar, E bar dot dl bar, the integral of, that is equal to E is equal to integral E bar dot dl bar. That same E is equal to, after substituting the phi as a Gauss law, same E is minus dou B bar by dou t dot ds bar. Got it, my students? Now in the left hand side, the line integral is converted to the surface integral. It becomes of del cross E bar dot ds bar. Del cross E bar dot ds bar is equal to minus integral of dou B bar by dou t dot ds bar. On both sides, there is a surface integral only. We can write this as del cross E bar is equal to, del cross E bar is equal to, get the minus also there, minus dou B bar by dou t. This is a Faraday's law of Maxwell's equation. Del cross E bar is equal to minus dou B bar by dou t. Got it, my students? See, the integral E bar dot dl bar is equal to minus integral dou B bar by dou t dot ds bar. Left hand side is converted into the line integral as surface integral. Del cross E bar dot ds bar is equal to minus integral dou B bar by dou t dot ds bar. On both sides, now it is the surface integral. Remove that surface integral, you'll get, and finally del cross E bar is equal to minus dou B bar by dou t. The another Maxwell's equation. So we already know that del dot T bar is equal to rho v, and del dot B bar is equal to 0. For monopole, there is no any phi. Is Gauss law of electric field, and is a Gauss law of magnetic field. And now we got another Maxwell's equation, that is a del cross E bar is equal to minus dou B bar by dou t. It's a Faraday's law. Faraday's law. Okay. See, the same equation represents the Maxwell's equation if B bar is not varying with time. Okay. Still now we discussed that this is a Maxwell's equation of time varying fields. If it is not varying with respect to the time, and it results in the electrostatics, the value is 0. So the B bar is not with respect to the time, not varying with respect to the time, dou B bar by dou t becomes 0. So integral d bar dot dl bar is equal to 0, and del cross E bar is equal to 0. Got it, my students?